how to apply Fourier analysis to solve ordinary differential equations. Okay, as an example, and especially we want to look at an example of forced oscillations, so that the force is a periodic signal to a system which can be modeled by an ordinary differential equation. Okay, so so before we can apply such a method, we have to justify some mathematical difficulties. Okay. So, all right. So let me address the idea of so we want to apply the theory of Fourier analysis or Fourier series to the solutions of differential equations. All right. We need to overcome, so we need to make sure the validity of the interchange of the limiting process and the differentiation operation. Okay, because later on you will see that. Okay. So you will see the validity of interchange of limiting process such as series sum. So if we consider trigonometric Fourier series, right? It's a series of functions, and we have convergence problem, right? We answered such a problem. So that the series sum actually is the limit of a partial series sum, right? So we define that, and so we have limiting process like to find a series sum, and also for solving differential equation we have to involve differentiation operations. Okay, so we have sometimes we have to exchange the order of limiting process and the differentiation, and we have to validate such interchange. Okay, and this involve usually the concept of uniform convergence. Okay, of a sequence of functions. Okay. The idea is pretty much like the uniform continuity of a function over a closed interval. Okay. In calculus, all right. So now I would like to define the meaning of uniform convergence. Okay. Now, so suppose we have a sequence of functions okay, defined on an interval I, okay, of the real line. Okay, so we have a sequence of functions. Okay, and such a sequence is said to converge, all right, uniformly on I to a function f on I. All right. So if for any epsilon greater than 0, there exists a positive integer n, okay, such that if we like the difference, all right, so this is the eta, right, of f sub n and the target function f, okay. This eta, we want this eta to be confined by epsilon. So epsilon can be selected very small, okay. And we ask that this is true for all n greater than or equal to capital N, and for all x in I. Okay. So the selection of capital N is independent of the point of in the domain I. Okay. So it's called uniform. So uniform on I means that this is true for all. So you can select just a capital N, and this capital N is good for all points x in the defined interval I there. Without the word uniformly, we say that this is sequence converge, all right, to a function I, all right. If for so let me give a remark. Okay. A sequence of functions, all right, on I, okay, is said to converge, all right, to a function f on I if for any point x in I and for any epsilon greater than 0, there exists, all right, a positive integer n, okay, such that f n x minus f of x less than epsilon for all n greater than or equal to n. Okay, so this n is dependent on the x. Okay, So that means that this is called pointwise convergence. So sometimes we may emphasize this definition by insert a road. So we can say pointwise. Okay. So you may add this word there. Converge to a function. So the conventional definition of convergence of a sequence of function to a function is in terms of pointwise convergence. So for every point, okay, this is the value, right? This is a numerical value. This is also a value. So for every given point x, this is a sequence of numbers, not a sequence of functions. Okay, and for this sequence of numbers, this sequence number will converge to this number. This number. So this is called convergence pointwise. Okay, and so this is depends on epsilon as well as x. Okay, so this is depends on x. Okay. But for here, the n depends only on epsilon. Okay, it depends only on epsilon. So the same n can be selected for all x in the interval. Okay. So this is called uniform convergence. So okay, so I hope you know the distinction. Also, remark, uniform convergence of a sequence of functions on I implies, of course, pointwise convergence. Okay? So uniform convergence is stronger than pointwise convergence. Okay? So you may neglect pointwise this word, just convergence. But the converse is not true, okay? So pointwise convergence does not imply uniform convergence. Okay, and now now we will state theorem 11.3.8. All right, so we let Fn just a sequence of differentiable functions on AB. Okay, so we assume that we have a sequence of differentiable. So Fn are differentiable functions, okay, defined on this closed interval. Now, if one Fn x0, all right, so this is a sequence of numbers, okay, right? So if the functions are complex value, then this is a sequence of complex numbers. If the functions Fn real valued, then this is a sequence of real numbers. So that this sequence converges for some x, for some point x0 in AB. Okay, right? So if we have two conditions, the first condition is that we can find a point x0 in this finite closed interval such that this is a sequence of function values. So it's a sequence of numerical numbers. Okay, so this is the numbers convergence. The second is that the derivative of Fn, okay, converges uniformly, okay, on AB. Okay, so suppose, all right, so this one, the first one, I think this is a minor condition. But this one, the second one is a major condition because it asks for uniform convergence of the derivative of Fn. Okay, we ask for that. So the derivative of Fn will converge to a function. Okay, on the same finite closed interval uniformly. Okay, uniform. So if we have these two conditions, then one, the original sequence of functions converge uniformly. Okay, on AB to a function f on I, first of all. Second that so Fn will converge to a function uniformly. Okay, the second is that the limit of this sequence of function Fn, f is differentiable. Okay, on AB, and its derivative. Okay, its derivative is the limit of the derivative of Fn for all x in AB. Okay, so we can rewrite this equation in the following way. All right, so what is that? This says that d dx, this is the differentiation operation. Limit n goes to infinity Fn of x. Okay? Because f of x is the limit of this sequence of function, right? Is equal to the limit okay. Now you can see we exchange the order of the limiting process and the differentiation operator. Okay, so this is the okay. So theorem 11.3.8 gives us sufficient conditions to make sure that the limiting process and the differentiation operator are interchangeable. Okay. All right, so look back here. First of all, we know that the original sequence of functions, when evaluated at a point x0, the numerical sequence converges. Okay, the numerical sequence converges is the weak condition or minor condition, but still essential. Okay. The second, this is a stronger, our major condition is that the first derivative or the derivative of f sub n converges uniformly, okay, to a function, okay, to some function, but we know it converges uniformly, okay, on the defining interval. Under these two conditions, then we know that the original sequence of functions f sub n converge uniformly to a function f. Okay, so this limit exists. And the limiting process is a uniform limiting process. Okay? So this one. And the second is that this limit, when we take the derivative, right? When we take the derivative is equal to the limit of the first derivative. So that means that f is differentiable at every point in this interval. Okay. Any questions? Okay. Yes, please. Oh, in Chinese. Okay. Okay. Okay, it's a little bit strange for me to speak in. Okay, I have to change more. 这里是说我们要找一个条件，条件是说，如果我有一个函数的序列 ，OK， 然后呢，它事实上是有极限的 ，OK， 也就是说它收敛到一个函数去这样子，收敛到函数去，然后我们就问一个问题，就像这个，就说它一开始的时候，对不对？我们就它收敛到一个函数去了。那我们想问的问题是说，那这个在这个我们叫做这个极限函数好了，它到底可不可以微分？是第一个问题嘛，可不可以微分？然后第二个问题是说，如果它可以微分的话，那它的导函数，对不对？可不可以用这个方法来求？比如说，原来的这个 fn 它本来就是可微分的啊，所以它本来就有导函数这样子，它本来就有导函数，所以我们就如果说通常来讲要求这个导函是比较简单的嘛，对不对？因为一般来说我们会知道这个 f sub n 是什么东西 ，right？ 然后呢，我们就可以知道它到底有没有导函数嘛，所以我们看看可不可以微分这样。那所以这个问题就在这里，就是说。因为通常我们有兴趣的是那一个什么，在那个极限，就是这个它的极限那边的行为嘛，这样子啊。所以说，既然每一个 fn 都可微，那我们问他，我们就问说，那它的极限是不是可微分这样子？可微分 ，OK？ 那如果是有可微分的话，那它的微分可不可以用这个方式来求这样子？啊，就是把它的这个导函数。来看看它有没有极限，如果有的话，它是存在这样。所以基本上，我们希望有这样的一个等式存在这样子，因为这个等式存在可以帮助我们去解一些问题的。好，那所以我们就要想办法。可是这个其实我们也可以了解，这不会永远都是对的。OK， 所以我们要找一些 这个充分条件，这个充分条件是在实务上很好用的这样子。Sorry， 在实务上是一个好用的这样子哈，所以我们就那个就发现呢，事实上有这一个好的定理啊。当这个定理我在那个lecture note 有讲它的 reference， 因为这个证明比较麻烦，所以我不会提供证明在这个，但是至少你要知道有这个定理，这样也就是如何用它。所以呢，这边就讲的，就事实上它就有2个条件你要符合。第一件事情是说就是说这个原来的这个 sequence fn 呢，它是可为的，换句话它都有导函数的。好，第一件事啊，这是应该给的了哈。然后过来就是说，对原来的 sequence 呢，它如果在某一点上去取函数值的话，所形成的这个数列就是 numerical sequence， 这个数列它会收敛这样子。数列收敛大家微积分有讲过嘛哈，所以我就不要重复了这样。第二条件是说，它的导函数本身呢，就是满足这个定义的条件，就是说它会收敛，然后它是怎么样？它是均匀收敛的这样子。好，均匀在哪里？在这原来这个 defining interval 里面，它的定义域里面这样，它是均匀收敛。但就是这2个条件，2个条件就可以了。那有这2个条件的话呢，我们当然就可以讲哈，就是说原来的这个 fn sequence 不只是在这一点它是收敛以外，它其实是整个函数呢会收敛到这个函数，然后它是均匀收敛的，所以它同样也有均匀收敛的这个事实这样子。因为一开始我们只是说它的导函数是均匀收敛的嘛，对不对？但是这里的话呢，它事实上是会均匀收敛到一个函数，我们称为 f 这样子。然后呢，这个极限这个极限函数 f 的话呢，它一定是可微分的。然后它的微分呢，怎么求呢？就可以怎么样？就可以利用这个方法求。也就是说，因为我们知道这个导函数本来就有极限嘛，因为什么？因为这边讲的嘛，它会 converge uniformly， 所以它当然就 converge 嘛，对不对？它会有极限。那刚好这个极限呢，就等于什么？等于 fn 的极限函数的导数这样子。条件是这样，这样还有问题吗？可以哈，不会。Other questions? Okay, so the proof. A reference. Okay. All right. Now, we state the theorem in terms of sequence, but our application is about series sum, right? So we have to translate theorem 11.3.8 to B, right? To B. Okay, so again, Fn it's a sequence of differentiable function on AB. Okay, if 1, the series, so it's a numerical series, converges, okay, for some x0 in AB. Okay? So when we say this is a differentiable function, right? So this is saying that this implies that the xn, okay, the partial sum sequence is a sequence of differentiable functions on AV, okay, which is defined to be so this is the partial sum function, right? So the corresponding partial sum function is also a sequence of differentiable function, because the derivative of xn is equal to the sum of the derivative of fk for k from 1 to n, okay? Because derivative is linear. And the series converge means that xn converge, right? So the series converge means that, so this is saying that the series converge means that the sequence converges, right? The same. And 2, the series summation n from 1 to infinity fn prime converges uniformly on AB. Okay, so the series converge uniformly is the same as the xn prime converge uniformly, okay? The sequence. Any questions? Series, the convergence of series is defined in terms of convergence of sequence, right? I think you have this experience in calculus. All right, so then 1, the series summation f sub n converges uniformly on AB to a function f, okay, and the second f is differentiable on AB, and f prime of x is equal to summation of fn prime of x for all x in AB. Okay. And this is just saying that d of dt sum of So this is the series sum, right? It's equal to dx, not dt. Okay. Okay. So series sum is also a limiting process. Okay. So you interchange the series sum. This is a limiting process, and this is the differentiation operation. Okay. Any questions? Okay. So this is a version for series. Now, uniform convergence is very important, right? So, we would like to provide a test. 11.3.c. This is called wire truss. Wire truss. Uniform wire truss test. Okay. For uniform convergence. Okay. Named after mathematician wire truss. Okay. So all right. So Fn is a sequence, okay, of functions. A sequence of functions defined on an interval I, okay, of the real line, okay, such that Fn of x, okay, is upper bounded by a number m sub n for all x in I. Okay, so suppose we know that for each sequence of for this sequence of functions, then for each function f sub n is upper bounded by a constant m. Okay, so okay, all right. So first of all, we know we have sequence of bounded functions. All right, and for each sub n little n, this function, this component function, is upper bounded by m sub n. Okay. Now, if the series summation m from 1 to m. So if we form for the upper bound, we form a series. If the series converges, means that the series sum is finite. Because of here, so m sub n should be non-negative, all right? So they are non-negative numbers. And the series sum of non-negative numbers either converge to a finite number or diverge to infinity. Okay, there are only two possible ways. Okay, and here we say that the series converge, so converge to a finite number. If this is the case, then the series of Fn converges uniformly on I. Okay, on I. Okay, so to test, because the second condition is a major condition, so we have to check whether the series sum of the derivative of S sub n converges uniformly. Now, Weierstrass test give us a very convenient tool. First of all, for each Fn prime, for each derivative of F sub n, okay, we find an upper bound, M sub n. Okay, right? We find an upper bound, and the bound we will use as small as possible. Okay, and then check whether this series sum is finite or not. Okay, use the upper bound to form a series and to check whether the series sum is finite or not. If it's finite, then this is true. And that's easy, right? This is a very convenient way to check uniform convergence. Okay, so this is very useful. Okay, so whenever we talk about Weierstrass test for uniform convergence, you have to know that it is this test, very convenient test. Okay, and so the proof okay. I give a short but clear proof for you. Okay, so I ask you to look at the proof. Okay, yeah, because I have to save my time. Okay, so okay, so please read the proof at home. Okay. All right, so now we have enough tool, okay, to deal with our problem of solving differential equations. Okay. All right, so consider a serial RLC circuit. I believe you learned circuit theory last semester or this semester concurrently. Okay, so if you have learned circuit theory last semester, then of course you know what I'm talking about. But you don't. I think you know this from general physics, right? In general physics, you have several chapters about electricity, right? So you know the capacitor, you know the inductor, you know the resistors. So consider a serial RLC circuit. Okay, so you may have this one. You may have like that. So you have an RLC circuit, all right? And you apply a voltage signal here, okay? And you want to know, so the voltage signal is given. So it's a driving force, right, to this oscillator, okay? So this is an oscillator, but damped. Why? Because you have resistance here. Without resistance, you have oscillator. Okay, so the energy will be pumping out of from C to L to C, etc. Right? So it's oscillation. Okay, so you will not consume electrical energy, if the resistance is 0. Okay, but with resistance, all right, the resistor will turn electrical energy to thermal energy, so that the energy will consumed. Okay, it will be consumed. Anyway, all right. So this is about electrical circuit there. So consider such a circuit, and in circuit theory, all right. So the current, all right. So the current I of t, right, is governed by a second order ordinary differential equation, ODE. Okay. Okay. If you didn't take ODE last semester, please raise your hand. So everybody have taken this course. Great, very good. Okay, because we will talk about ODE a lot. Okay, in this chapter. That's good. All right, so so we know that the inductance times the second derivative of the current signal plus the resistance times the first derivative of the current plus 1 over the capacitance of the current is equal to the derivative of the voltage signal here. Okay, so we have this one. Okay, we have that. Now the general solution, right? So the general solution of the above ODE, okay, is the sum of a homogeneous solution and a particular solution. A homogeneous solution is a solution such that the driving force is 0. Remember that? Good. All right. So that the general solution is the sum of a homogeneous solution and a particular solution. And the homogeneous solution, because it's second order, so it has 2 undeterminants. The degree of freedom is 2. Okay? The degree of freedom is 2. So initial condition, all right, 2 initial conditions will give us a unique solution. But without initial condition, our boundary conditions, then you have 2 degrees of freedoms, okay, for the homogeneous solutions of the ODE, okay, and also you have to find a particular solution, okay. Now, so this is about ODE. I just state the ODE and things. The ratio R and L. So when you divide L here, all right. So this constant, this coefficient, when we normalize the highest order, so we divide L here. Now divided by L is greater than 0, okay? Because resistance, inductance, all right, are real, are positive numbers. So this ODE, okay, govern a damped system. All right, so it's a damped system. So that any homogeneous solution, okay? The reason why you have homogeneous solution means that the reason why you have current flowing the circuit when the driving force is 0 is because why? Because the initial energy in the capacitor and in the conductor. If the initial energy in these two components are 0, then the current is 0, nothing. So 0 is also a solution, right, of the homogeneous differential equation. But if you have initial energy, all right, at the time t equals 0 in the capacitor or inductor, then of course you have a current flow, of course. But the current flow, because of the resistance, right, all the energy, the electrical energy, will dissipate through the resistance into thermal energy. All right, so the current will eventually goes to 0. So it's called a damped system because it would damped to 0. Okay, all right. So that is, you get the idea from circuit theory. All right. So that any homogeneous solution, so you know they are homogeneous solutions. All right. Let me recall that. Okay. So they are homogeneous solution depends on because this is two orders, so depends on the discriminator. So this is minus R divided by 2LT. All right, so this is the exponential decaying circuit. C1 undeterminate exponential square root of R squared minus 4L divided by C divided by 2L T plus C2 E minus square root of R squared minus 4L divided by C and 2L T. Okay. If R squared minus 4L divided by C is positive. Okay. But if it is 0, if this is 0, then the homogeneous solution will be times a linear function. Okay, so this is the degenerate case. Okay, and if the discriminator is negative, then we have oscillation. C1 cosine square root 1 over LC minus R square divided by 4L square T plus C2 sine function square root 1 over LC minus R square and 4L square T. Okay. So remember, we have 2 degrees of freedoms because it's a second order ODE. All right, so you can see the homogeneous solution will vanish. Okay, as t goes to infinity. Okay, so this exponential will goes down exponentially, even though this is a linear function, but the exponential function decay much faster than linear function. Okay, so this term also goes to 0. Okay, no matter you can see here. Okay, so right, so that means that without the external force. Okay, so without the internal force, E prime T, the E prime t here, the exponent force, the current of the serial RLC circuit will diminish, okay, to 0, right, exponentially fast. Okay, all right, so that's as t goes to infinity, the solution of the ODE, okay, approaches the so-called steady-state solution. Okay, and this is steady-state solution, which should be a particular solution. Of the ODE. Okay. All right, so this is a description of. All right, so our purpose is to solve the steady-state solution. Okay, a steady-state solution. When the voltage signal is periodic, okay. Right. So I think I have to stop here. So it's any questions? No. Good. Okay. So please